Welcome to the part 3 of the first tutorial. Today we'll discuss NumPy and Pandas. So let us get started. So notice that in the current directory there is another file called mechanicalprops.kaggle.csv. So we'll be importing this file while we run the Jupyter notebook. Let's get started with 00B, NumPy and Pandas. Previously we discussed how to write functions and how to write classes. Now turns out some codes require a lot of classes and functions. So one way to arrange them is using modules and packages. Modules are usually .py files that contain pre-written classes and functions. And then modules can be arranged into directories. These directories are called packages. And usually these packages contain underscore init underscore dot py file. So we need not go into the details of this. And library is an umbrella term that represents a collection of related packages and modules. Some examples are NumPy, Pandas, scikit-learn, Torch, etc. So let's see how to import a class C from a module m.py that is located in a package P, and we'll create an instance of this class C called C object. So there are multiple ways to do it. 3 of it are shown here. So our package is P, module is M, the file is M, and the class we want to import is C. That means the class is pre-written in the module M and we want to use it in our current code. So we can write from p.m import C. Now the code recognizes C as a class, and we can go ahead by creating an object C object by using C. Now the other way is to give an alias to the class. So for example, you have created a class in the current notebook that matches with the name of the class you want to import. So you can give a nickname or an alias to this class as such. So from p.m import C as req class, required class. So now you can call C by calling req class. So the C object is now becomes req class brackets. And the third way is, say you want to import a lot of classes from a given module. So you can import, you can give an alias to a module as well. So for example, I want to call this module M as reqm, required module. So I can say import p.m as req mod, and then to access the C, the class C, I can use req mod dot C to access this class and create the object C object. Now let's get started with two very necessary packages, NumPy and Pandas. So NumPy forms the basis of many classes and functions that we are going to use, and PyTorch and scikit-learn are built on top of NumPy, as well as Pandas is also built on top of NumPy. So let's look at NumPy first. Before starting, let's import NumPy as NP and Pandas as PD. That is the conventional aliases for NumPy and Pandas. Now let's get started with NumPy arrays. So NumPy arrays are a class within NumPy, and let's compare these NumPy arrays. So these NumPy arrays are very similar to lists. Now let's compare the default Python lists with NumPy arrays. Let's create two lists, A and B. Both lists contain 5 integers. Let's run this. Now, as you already know as of now, that these lists are actually classes, and they have the defined rules of additions, appending an object to a list, etc. Now let's look at what happens when we add two lists. So let's add A plus B and see what's the output. We see that all the elements of the second list, 1, 5, 3, 5, are appended to the first list. So A plus B combines two lists. And this is slightly different from append. For example, if we do A dot append, append B, what you'll notice is the entire list B will be appended to A. So let's print this. Let's print A after this. So after A dot append, A will be modified. After we print A, we see the entire list B is appended to A, but A plus B adds all the elements of B one by one to A. So this is how addition is defined in lists. Now let's create a NumPy array. So to do that, we can convert a list to an numpy array. So there's a function np.array. Note that np.array is a function, and you can notice that all the letters in array are in small. That is the naming convention of a function. So we use np.array function, and within the brackets we pass the list which we want to convert into a numpy array. Now after doing this, let's print a and let's print the type of a. So turns out a looks like a list, but the name of the class or name of the object is numpy.ndArray. Now let's see how numpy array addition is different from Python lists addition. So let's create a list A, list B, and convert these two lists into arrays and store them in variables A array and B array. We print A array plus B array. Now we notice here that when we add two arrays, the result of addition is element wise addition. So for example, 1 gets added to 4 and the first element in the addition becomes 5, and so on. And that is different from lists addition. So if we do just A plus B, the list just get appended. So that is how numpy arrays are different from lists, and you can notice that the numpy arrays follow addition rules for vectors. They get added like two vectors. So we represent vectors in our codes as numpy arrays. And similar to vectors, we can also represent matrices as numpy arrays. So let's take a look at a matrix representation. So let's create a list of lists called mat underscore. So basically you can see that this is a list, it's enclosed within square brackets, but this list, the elements of this list are three other lists. So that is list number 1, list number 2, and list number 3. Every list has 3 numbers. So we represent this list of lists as mat underscore, and then we pass this mat underscore into np.array and store it as mat, and let's print mat. Let's print it out, and let's print the type of mat. Print type mat. So once we run this, we see that again mat looks similar, but it's again a numpy.nd array type object. So even matrices can be stored as numpy nd arrays, and they also follow multiplication addition rules of conventional matrices, and we'll look into that a little bit later. So for now, it's important to note that this is a very important function, that we can create random matrices by using this function randint. So that is within the module random. So np is the package or library. Within this package, there's another directory random. So that's also another package, and .randint is a function inside that package. So np.random.randint will create a random matrix of a given size. So you can mention the size within this attribute and provide it a tuple. So we have provided a tuple 4, 3, and there are two other keywords. One is low, that is what is the lowest integer in your matrix, and high is what is the highest integer excluding the high. So if we create this matrix, there will be numbers that contain 1, that are 1, but there will be no numbers that contain that are 10, but there will be numbers from 1 to 9. So let's make this random matrix A and print A out. So we see there are 4 rows and 3 columns as we provided in the size. And another important thing to notice is if I rerun this, so just notice that the numbers are 8, 6, 5, 9, 4, 7, etc. If I rerun this, the numbers change. So it generates random numbers, and every time you run this, you might get different numbers for every element. Now at times it becomes necessary that you want to reproduce your code. So say you want to do some analysis with matrices and you want others to verify the validity of it. So it's necessary that others reproduce the exact matrix that you created. So one way to do that is to use a random seed. So you can do that by running this line of code, that is np.random.seed. So that sets a seed value that is 10, and after that, whenever you run this any random number generating code or any code that has to do with randomness, it will reproduce the same random sequence. So for example, let's set this seed as 10 and let's rerun the code here. So it always, so it generates 5, 1, 2, etc. And every time I run this, it generates the same matrix because we ran this code just after initiating a random seed of 10. But notice that if I run this code again, that is the second time I run it after generating a random seed, it will give a different matrix. So this matrix is different from here. Again, the third run will give another different matrix. So this is again slightly different, but the nth run, always the nth run after generating after fixing a random seed is always fixed. So that's how we ensure reproducibility in our code. Now another useful function in NumPy is checking the dimension of a matrix. So you have a huge matrix and you want to find out how many rows and columns are there. So you can use np.shape and pass that matrix or vector. So this is basically a numpy.ndArray object to this np.shape function, and it will give you the shape of the matrix. Let's pass A here, that's the random matrix we generated, and we get 4, 3. Basically there are 4 rows and 3 columns. And now let's look at how to access a certain data type in your matrix. So let's say our matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9. And indexing is very similar to lists in Python. And for a 2-dimensional ND-array, that is a matrix, we have to provide 2 indices. And the indices again start with 0, both for rows and columns. So let's say we want to access 6 in this matrix. So that comes in the first row. So this is the 0th row, this is the first row, and this 6 is again in the second column. This is the 0th column, this is the first column, this is the second column. So if I want to access 6 here, I type within square brackets mat 1, so that gives out 6. Also, you can fetch an entire row or an entire column. So let's try to fetch the entire last column, that is 3, 6, 9. So basically we want to fetch all the rows in column 2. The way to write this is like this. So we want to fetch all rows, that is a colon mark, and column number 2. So just we provide comma and then and the number of the column, and if you print this out, it gives out 3, 6, 9. So this is the column vector of this matrix, the second index column vector. Similarly, say if you want to access all the columns of say the first index row, we type this and we get 4, 5, 6. That is all the columns of the first index row. Again, this is accessing a specific element of matrix A. So A is 2, 5, 3, 7, 8, 9, etc. We are accessing the 0th row and the second column, that is 3 here. Another important method is the reshape. So let's look at A here. The shape of A is 4 rows and 3 columns. So that is 4, 3. Let's print this out. np.shape A. So if we run this, it gives 4, 3. Another way to access it is just access the attributes. Attribute are variables. Whenever you access variables, you need not provide this brackets. So these brackets are representative of classes or functions, but variables do not need brackets, and a.shape is a variable. So if we run this code, we again get 4, 3. It's another way of getting the same information as np.shape A. Now, basically there are 12 elements here, and say we want to reshape this matrix such that there are 6 rows and just 1 column. So we can do that by using the method called a.reshape, and this method takes in a tuple, and this tuple, we set this tuple as 6, 1, and if we run this, okay, so because there are 12 elements, if we have 6 rows, we need to have 2 columns here. So let's make it 6, 2 and run this. So we get the same information as in matrix A, but in a 6 by 2 matrix, and the order of numbers is such that all elements appear one by one row wise. So 2 and 5 appear in the first row, then 3 and 7 appear in the second row here, and so on. So as you notice, if your provided dimensions are different from what the matrix can accommodate, the method will throw an error. So for example, if I do 6 comma 3 and I run this, it says cannot reshape an array of 12 of size 12 into 6 comma 3, because 6 comma 3 needs 18 elements. Another nice trick with reshape is, say you're sure about how many rows and columns you want, but you do not want to calculate how many so how many columns or rows you want to get with them. So for example, with these 12 elements, I want 6 rows, but I do not want to calculate. I want to be lazy and not calculate how many columns that leads to. So I can always provide -1, and it will take care that it puts all the other elements in a suitable size of the matrix. So for example, I want to create a 3 column or a 4 column matrix. So I can provide 4 here, not calculate how many rows I need. I can provide -1 here and run this. So it basically creates a 4 column matrix, and it adjusts the number of rows to be 3. So that is with generating random matrices. You can use that to also generate random vectors, so one-dimensional matrices or column or vector matrix, column or row matrices. And now let's look at another function that is very important to systematically generate a vector. So for example, I want to create a vector that starts with 1, ends with 10, and all the in-between numbers are integers. So one way to do this is to use the np.arange function. So let's look at how np.arange works. So it takes the lowest value of your vector, then the highest value of your vector, and the final argument is what is the difference between two successive vectors. So to get more information, you can place your arrow here, place your cursor here and press Shift plus Tab. So this gives you all information about the arange function, and that is valid for almost every well-written Python module or package. So you do not have to remember what a function does. You just have to know that there exists a function like this, and then call it and use Shift plus Tab to find out what arguments you should give or how you should use it. So for example, this np.arange describes that returns evenly spaced values within a given interval. And how do you provide the interval? The arguments are given here. So it provides an argument called start, an argument called stop, and an argument called step. There are other arguments as well, but they take their default values. So we start with 1, end with 10, and the step is 1. And it's important to note that the stop, that is 10 value, is the end of the interval, and the interval does not include this value. So we'll get numbers from 1 to 9 in increments of 1, because we have set steps to 1. So let's just run this, and that's what we get. So 1 to 9 in steps of 1. So if you want to get till 10, so we increment this to 11. 11 won't be included, but 10 will be. So now we get an array starting with 1, ending with 10 in increments of 1. Another similar function that has slightly different usage is np.linspace. So similar to np.arange, you can provide the start and the end, but the final number is not steps, but the total number of elements in your array. So if I want this same array, I can use np.linspace, and instead of providing 1 here, I can provide 10, because there are 10 numbers between 1 to 10. So if I run this, we get floats here, 1 point, 2 point, 3 point, etc. But it starts with 1, ends with 10. The other difference is in arange, the second argument is not included by default, but in linspace, it is included in your array by default. So let us say we want to convert these numbers into integers instead of floats. So how to do that? We can get this information by pressing Shift plus Tab. So these are the arguments. Start, so we have provided start to be 1, stop to be 10. Num by default is 50. So if we do not provide num, it takes 50. So let's try to run this without this 10. Let's just provide 2 arguments. and we see it creates 50 numbers. So 3, 4, 5 columns and 10 rows. It starts with 1, ends with 10, and there are 50 numbers in between. So let's just go back and provide this as 10, shift plus tab. And then there's an argument called d type. D type is set to none. Let's see what should be the, what data type should be provided as D type, so that we can scroll down and see. So D type is optional. The type of output array. If D type is not given, the data type is inferred from start and stop. The inferred D type will never be an integer. So float is chosen if the arguments would produce an array of integers. So if we want these to be integers, we just have to set D type equal to int. Let's try this. Yes. So now our numbers have become int. So this is also a demonstration how you need not memorize how to provide arguments to a function. You just need to know that a function exists, call it and press shift plus tab and figure out how to use that function. So NumPy has also an attribute or a variable inside it called pi. So if we use np.py, it gives out a rough estimate of pi up to some decimal numbers. Now let's create a array, NumPy array, that contains values 0, pi by 6, pi by 4, pi by 3, pi by 2. So basically I've provided all of these in a list, and we have passed this list into the np.array function, and we have stored this value in variable a. Now let's pass this variable a into np.sign and see what it does. So we see that we get a same dimensional array, but all elements, all numbers within the array have been transformed into their signs. So sign of 0 is 0, sign of pi by 6, that's 30 degrees 0.5, and so on. So to verify that, we can also use the np.square root function. So that takes in a number or an array. So basically np.sign can also take a number and give you the sign of it, or it can take an array or matrix and it takes the sign of all the numbers within the array or the matrix. Similarly, all other functions within NumPy work like that. For example, to np.square root, if I pass 1 by 2, it takes the square root of 1 by 2. But if we pass an entire array, say A array, it takes the square root of all elements within that array, like this. So let's stick to 1 by 2 here. And turns out this value is similar to this, that is sine of pi by 4, sine of 45 degrees. And square root of 3 by 4 is 0.886. So that's also correctly evaluated, sine of 60 degrees. And now let's look at how to take dot products of two vectors. So A is np.array 1, 2, 3, B is np.array 1, 3, 2. If we take the dot product, that means our result should be a scalar, and the scalar should be the sum of the products 1 into 1, 2 into 3, and 3 into 2. So that is 1 plus 6 plus 6. So we should get 13 here. So that's how it works. So if you want to take the dot product between two vectors, you can use the first vector dot within brackets the second vector. So one way to generate an identity matrix within NumPy is to use the np.I function. So identity matrices are always square matrices. So you just have to provide one number and it creates an n by n identity matrix. For example, if we provide 5 to np.I, it creates a 5 cross 5 identity matrix. Now we can also do matrix multiplication. So matrix multiplication is same as doing a matrix the dot method and then providing the other matrix. So let's say we have created a matrix A and an identity matrix B multiplied by 2. So let's print out A here. So this is how A looks like, and B is 2 into np.I3. So that is 2 multiplied by identity matrix of dimension 3 cross 3, that is 2, 2, 2. So of course, if we multiply these two matrices, we'll see that all numbers in this matrix are multiplied by the diagonal element of the identity matrix, so 2. So if we do this A dot B, yeah, we notice that 1 becomes 2, 2 becomes 4, 3 becomes 6 here, and so on. So for now, we'll stop our discussion here and we'll continue the rest of pandas in the next tutorial. Thank you for joining.